Very good. So, and maybe I'll just make note here of the title here, Expecting the Unexpected with AI at Particle Colliders, which will give you a bit of a hint that one of my main interests with collider physics is looking for beyond the standard model, new exotic stuff that's out there. And that motivates a particular kind of AI that I will get into. Okay, so to do the really quick motivation, I want to go back to 2012, which might seem like a random year at first, but super influential year for both of the sort of fields that we're going to talk about and bring together in this conversation. One of the big things that happened in 2012, we found elusive particles seen as key to the universe, according to the New York Times. Of course, that was the standard model Higgs boson, which had been, we'd been waiting about 50 years since it was first predicted in 1964 by Higgs and Engler. And obviously, as a result of waiting all that time, this is a, cause for huge excitement in the field. Completely, the last predicted particle in the standard model, and really changes a lot of what comes next in particle physics. Up until the Higgs discovery, we had been sort of going through this beautiful theory and just checking boxes off of particles to discover. Once you have that last standard model particle incorporated, you're in a bit of the Wild West. So that changes the attitude, I think, to what looking for new physics means or building a fundamental particle model that includes all of the observable phenomena in the universe. At the same time, there was from the same year a similar article from the New York Times. Scientists see promise in deep learning programs, which I think is really cool to realize that these were these two, technological revolutions that were coming up at the same time. And in particle physics, we were some of the, earliest adopters of very early machine learning, going back to like the 90s. People were doing super simple, complex linear regression type algorithms that were the basis for what would become deep learning with the advent of more computation. Now, of course, we're doing, as I'm sure you're all aware, crazy things with trillion parameter foundation models and billion parameter gradient descent and all of that. And that brings in also the third aspect of what I want to cover here, which is the importance of the computation platform choice. That the more we can sort of push calculations through pieces of silicon, the more deep learning we can do, and then how that's going to come back, of course, and impact the physics. So it's been over a decade since the Higgs discovery. We have not, I'll give you a spoiler alert right now, there's no evidence, strong evidence for beyond the standard model physics, but there's a lot going on nonetheless. And partly why it's such a still active area to search for is that Higgs physics is very closely connected to lots of other interesting paths for where new physics could be hiding. So this is a nice graphic that came out of the SNOMAS community planning process that happened in 2021 and 2, I guess that shows how Higgs physics is related to the thermal history of the universe, the origin of symmetry breaking, naturalness. The Higgs itself could be composite. It could have multiple partners, charged Higgses and heavier Higgses, um, connected, of course, to masses and flavors and the stability of the universe. So I think, since we haven't found some crazy new exotic thing in some time, people get a little pessimistic sometimes about direct searches for new physics. And I might argue the opposite, that it's never been a better time to look for new physics because we have this new particle in our hands that we can use to characterize and explore all of these different things that hopefully connect us up to these fundamental questions that we'd like to answer. Okay, so our latest and greatest tool for doing all of these great searches, of course, is the Large Hadron Collider. This is a 27-kilometer proton accelerator sitting across the French-Swiss border. So we're bringing these particles up to super high energy, colliding in a controlled environment, and hoping to turn all of that center of mass energy into mass of new particles that we can produce. And in order to determine that we did produce maybe some exotic new particle, some heavy exotic new particle, we build these complicated detectors around all the interaction points to collect all the information that's needed about what happened after that initial collision, and then doing some kind of forensics effort to reconstruct it and piece it all back together to try to do a statistical test of was there something new in the moment those protons collided that subsequently decayed or it left other hints in your detector. So that's kind of the main mechanism of what we're doing when we search for new physics is combing through these billions and billions of proton collision events and trying to see if there's evidence of something novel or unusual that could point to new physics. And so this is an example of what such an event actually looks like. I guess by actually, this is, okay, reconstructed like it's an event display. But we have different subsystems of detectors that collect different kinds of signals. So in the innermost region, this is where things are the most busy. There's a lot going on. We're collecting tracks from charged particles. We have calorimeters that collect energy deposits. These long lines here are muons that make it all the way out. And so you can uniquely identify different species of particles produced in the collision, and that helps you in this effort to see if something interesting happened in the event, something unusual. So I want to zoom in on one particular use case that I've spent quite some time thinking about that is particularly useful for the artificial intelligence application, which are with jets. So a jet is a type of object that you can get in your initial proton-proton collision. And it is a it is a byproduct of the fact that we have confinement in the standard model. And so if you produce a quark or a gluon in that proton-proton collision, which we do a lot because we have high energy protons colliding together, that it will not just propagate through the detector like the muon and leave some nice neat line. It's going to pull friends out of the vacuum. It's going to hadronize with the detector material. And so you end up with this signature that is a combination of tracks in the inner detector, so individual lines for those charged particles, and then clusters of energy deposited in the calorimeters. And so we do clustering of both those signals, correlate them together, and we call that a jet. And so the reconstruction is actually done by putting these constituent particles together into a cone-like shape. And so these jets, not only are they super common just because they're arising from quarks and gluons, which are the most produced particle in these collisions, it's also very connected to lots of potential new physics. Lots of new physics is expected to couple to quarks and gluons. I'm being intentionally really vague about what kind of new physics because where I'm going with this is that it doesn't really matter for the type of AI that I want, that I've been, specializing in. And I think the motivation for why we can be so blasé about the model is that we don't know what we're looking for, right? If we knew what new physics looked like, this would be a lot easier. In fact, it wouldn't be a problem at all. Uh, I think that we are trying to expand our AI techniques to accommodate the fact that one, it takes a long time to look for a particular model. These analyses take years, so we want to be more efficient with how much phase space we're covering, and we don't know what we're looking for. So we would like an AI technique that can allow us to learn what the standard model, the typical quark-gluon interactions or typical particle events look like, and then find things that don't look like that. And that's going to be our new starting place for beyond the standard model searches.
Hi, Julia.
Yeah.
So can I ask a question
Yes.
before we go? So, I'm curious about like what are the jets looks like in the data set? I mean, so of course you have a lot of signals on the LHC after the collision. So what kind of data, like, do you have like intuitive picture of how the signal and data looks like? Because that's important for the numerical analysis, I think.
Yes. Yeah. So great question. I think I will get into it maybe in a couple slides, but to answer
Mhm.
in brief, I think you mean like what are our options for input modeling for
Mhm.
these types of things? And the community has actually gone through many. So for example, when I started doing research into ML for jets, we were looking at the jet as a sequence. So like you start, so here you can see in this cone, we're talking about a list of these constituent particles, each of which is described by a four vector. So that's
Oh.
maybe one simple way to do it. You could just put a list of four vectors into your model, but if there's
Mhm.
any like relationship between them or correlations that are different between them, you'd want something like recurrence or attention that can accommodate those types of features. So when I started doing this, we were using recurrent architectures, and then those completely fell out of style because then we had the transformer. So now a lot of querying and modeling of these jets is done with transformer level, but in the end, you're talking usually about particles that are each described. So maybe 20 to 100 particles per jet with
I see.
some sorting based on their momentum, for example. And then they're each described by a set of features.
I see. Thank you.
Cool. Okay. Very good. So what I was alluding to, the type of machine learning that I was kind of getting into that I've been thinking about that answers this more general question about looking for new physics is anomaly detection. So my working definition here is that we're trying to build a model that will identify certain elements in the data set, not in your typical supervised classification way, not because you showed the model cats and dogs and it learned to separate cats and dogs from a labeled data set, rather that you're just streaming data to it and it will figure out what is inconsistent with that model that it learns from just seeing what the data looks like. And so a really common way to do that, to implement this in machine learning, is to train an architecture to reconstruct its input. So if you guys are familiar with autoencoders, which I bet most folks are, that's where I'm getting to. But to describe this purely in the abstract, imagine that you're taking some model that is reconstructing its input and you're training it over fish, as you might be interested in doing. And so you're streaming in all of the different fish in this group. If you're doing that, since you don't know this is, imagine this is data, you don't have any truth label you can assign to these sources because you don't know what kind of fish it is, right? So that's completely unsupervised training. And as you are going through this training data set, your model is going to get better and better at reconstructing the primary features of this data set. So for example, it will learn how to reconstruct the color blue very accurately. It will learn how to reconstruct a fish swimming to the left, such that when you then stumble on the anomalous event, it has no idea how to reconstruct this. The weights in the model have not learned to reconstruct red or a fish swimming to the right. And so it will completely fail at this reconstruction task. And that's the flag that I'm interested in. That allows me to build a single classifier variable where the bulk of my normal looking data, what it often saw in training, are accumulated at one side. And I have some long tail out to high reconstruction error where my anomalies are hiding. So this is gold in particle physics because I want to be able to threshold on certain variables that will throw out the overwhelming background and preserve the stuff that I might be interested in. So these rare outlier events are what's going to become my primary source of hint that there is beyond the standard model physics in some of these events. So let me bring this and apply and think about the application specifically to jets. So a background jet, a typical jet originated by a quark or a gluon, has a sort of homogeneous pattern of energy deposition across the cone. There's no, this is just based on the parameters of how QCD particles shower. Whereas my new physics, something that is signal-like, might have some different features that are kind of obscured within that jet cone. So for example, maybe I had some heavy new particle decay to two daughters or three daughters. And if it was produced with some boost, because we have a high energy machine, they all ended up collimated. And I actually have hotspots of energy deposition corresponding to daughter particles within that jet cone. So this is something that could mark a jet as anomalous or unusual and be worthy of scrutiny. This one on the right here is a type of signature I got interested in of dark jets, where you have some complex dark sector, multi-species dark sector that has still an SU3 symmetry. And so you can have full, color-like showering within the dark sector that is interacting with the standard model. So you end up with one of these jet cones that has some invisible energy and some visible energy because it's partially carried away by dark matter. So if I wanted to do a search for something like these dark jets or one of these other jet topologies, I could build a supervised method to focus on these two different prongs or three prongs or whatever. Or I could try to build a single classifier based on anomaly detection that is sensitive to all of them at once. Because we are inherently lazy and we don't want to have to do 6 analyses to get to new physics, right? And so here's how the autoencoder input modeling would work if I think about the jet modeled as that set of constituent particles, is that I would feed it into my encoder, which has to do a lossy compression of the original input features that I've chosen. And then you have a decoder stage that will start from that lower dimensional representation of the data and try to generate something of the original dimensionality. And then I'm checking the reconstruction error between input and output, using that as the loss to force it to do a better job reconstructing, which is the same thing as saying that it is encoding more salient information in the latent space. So this bottleneck of information is essential to getting this whole anomaly detection aspect to work. And so when you train over the LHC data set, you're going to mostly see jets that look like this. It's going to learn that those are not anomalous. It's going to yawn and say, I've seen a million of them. But that in fact, oh, sorry, I skipped a slide, but if you show it some anomalous jet, like one of these three models, it's going to have that flag go up and say, I can't reconstruct this, therefore, please, note that you can look at this in more detail. So this is sort of the abstract way to describe a type of anomaly detection that has become common. These are a couple citations of recent works that came out from Atlas to, if you want to, read more about how these analyses are done in detail. There's anomaly detection beyond autoencoders, but there are also a lot of autoencoder based searches that people are doing now to look for new stuff. Okay, very good. Then let me move to the hardware section. And in order to, I'm going to start with basically the same idea of running that autoencoder and doing that anomaly detection, but moving it earlier in the data acquisition of the experiment. And the reason that that's relevant is because to get to that data set that comprises our offline analysis, where we can do these cool new searches, our data has to go through a couple stages of filtering. So we start right at the front end with the ASIC that's collecting information from your active sensor in the detector. And then we have this trigger system, which is a real-time decision algorithm that has to aggressively filter the events that are coming off of the front end. And that's because our data rate is just wild, and there's no way that we can save all of those events that are produced in the LHC. So imagine you have one of these, any type of event with all these different particles that's produced at the front end, and you need to make a decision about it. We need to decide either it is potentially interesting and we want to be able to save it to disk to do more analysis on it, or it's not interesting. We've seen it a million times before. It's perfectly usual, typical standard model stuff. It's soft. Most of the collisions are actually just soft pile up quarks and gluons. We don't need to write them to disk. We don't need to burden our storage system. We want to save only the stuff that could be interesting. And this filtering, like I said, is pretty aggressive. We are only allowed to save less than 100th of a % of all of the total events produced at the LHC. So that gives you a sense of, number one, the data rate that we're coming up with, and two, that you really need to get pretty lucky to produce something that could be, worth analyzing later. You need a really good hard scatter proton-proton interaction to produce something massive enough that we're interested in adding to one of our analyses.
Sorry, I have another question, Julia. Um, so sounds to me like the way to do the encoding and decoding and try to fill out those anomaly, these are actually quite rare events in the collision, right? You're trying to figure out what are the sorry processes that is almost impossible to happen. And our physical goal is actually find the event that beyond standard model. So are these two like these two criteria are consistent with each other? Like always, you always have like the beyond standard model thing is quite rare thing. Is that a case?
Yeah, so I think um, the important thing here is what we mean by rare. Um,
Uh,
so I could say qualitatively that we believe that beyond standard model physics must be somewhat rare, or else we would have seen it already. Like, and there's many reasons to believe that we're talking about very low cross-section processes because of maybe constrained phase space, small coupling, say, between standard model and hidden sector, um,
Mhm.
things like that. Uh, but I also want to note that these anomaly detection algorithms,
Mhm.
like even like WZ production or top production or Higgs production are very, very, very rare
Uh-huh,
if you're
uh-huh.
looking at the entire set of events that are produced in the LHC. And so I'm about to get into how we apply anomaly detection to the trigger. And in
Mhm.
fact, we want like some of the arguments that you can make for why you'd want to run such an algorithm in the trigger is that it actually can enhance efficiency to known standard model signatures as well. Because the anomaly detection algorithm just sees billions and billions of like low energy pileup events that a W or a Z or a Higgs looks anomalous, and it could just be recognizing that anomalousness in a different way than the typical trigger algorithms. So you're enhancing efficiency to all these other hard scatter processes. The real anomaly, if you're looking at all the events, is hard scatter processes, high momentum
I
stuff. And
I
so
see.
that covers, yeah, heavy byproducts of beyond the standard model physics, and it also can cover just regular standard model stuff.
Mhm. Yeah, because the reason why I ask it because you mentioned here, like most of the data will be dropped, not saved because it's too long, too much data, and the thing that be saved will be determined by this trigger, the hardware trigger or software trigger. And is that possible? Like you just leave out beyond standard model signal if that's just something not so rare.
Exactly. Yeah, this is exactly the motivation. So maybe in a couple more slides, I'll get into sort of the existing trigger algorithm and then explain why anomaly detection can help and exactly what phase space it covers, and maybe that'll, yeah, I think kind of build on the question you're asking. Cool. Thanks. Okay, right. So as we are just sort of getting into, we we are forced to do this filtering because we cannot possibly look at everything. And so but it's incredibly important because whatever this algorithm chooses, that's our whole data set. So we have to be really careful about what we are saving because if we're throwing out something interesting, we're going to feel very stupid at the end of the LHC that we had it maybe all along. Uh, so that's one of the challenges, is doing a good job at designing that algorithm. The next challenge is that we have very, very, very little time. So the LHC is running at 40 megahertz. That means we have 25 nanoseconds, and a new event coming in every 25 nanoseconds. And so this whole data acquisition pipeline is structured so that the hardware trigger, you have a couple microseconds maybe to make this decision. Then you send that filtered output to another level of trigger that has maybe like a millisecond. And that in the end is the rate at which we are sending out events. We're saving one every millisecond, down from 40 million a second. And so if you want to bring machine learning into this, uh, we have to be very, very clever. So just to kind of give a little bit of context to what so a lot of this microsecond latency of this trigger is actually used up by other stuff, in fact. And so we in the end are left with like a couple of nanoseconds to put in a full decision-making algorithm to take in information about the event and make a decision. So just for context, that's about 1 million times faster than typical human reflexes and about 1,000 times faster than a camera flash. That's the time scale we're talking about. When I first started working with some of the engineers here at SLAC, and I said we need a machine learning algorithm to run in a couple nanoseconds, they laughed at me. Like self-driving cars don't have this kind of like no one is working on nanosecond timescale. This is really like at the very edge of what's possible to implement kind of stuff. So here's kind of the premise for doing real-time anomaly detection, and it's sort of presented here as what we are gaining on top of the traditional trigger menu. The existing trigger algorithms, the vanilla type of algorithm that you can run in nanoseconds, it's a pretty blunt instrument. And what we're basically looking at is the energy scale of the event. If I have high energy particles in the final state, I can imagine there was a hard scatter in the initial collision, and that could be a hint of that had that interesting heavy new physics. But if there is new physics hiding below those energy thresholds, say it's soft new physics, it's some exotic model that doesn't get above those thresholds, we could be producing it maybe even at very high rate. And we've just been throwing it out this whole time because we have this very simple trigger process that we have to apply given the time constraints. So the idea of the anomaly detection trigger is that I can have some other algorithm that is maybe a bit more agnostic to energy scale that can probe below those energy thresholds and start to write out completely new events for me to do my analysis. The real trick is, can I take that autoencoder principle and can I run it in less than 25 nanoseconds? This is like the big, significant question of doing this. And so that brings us into the domain of fast machine learning, where we're really trying to co-design the machine learning algorithm for the hardware platform that it will run on. So if I want to get to nanoseconds, I'm going to need something better than a CPU or even a GPU, which will only get you to about a millisecond of latency. So we're talking about really customized, super efficient hardware platforms. And we're also going to need to make the models very small. I want to do as little math as possible because every bit to bit operation I have to do is going to take time and it's going to take resources. So there are a couple common ways that you can do this in so-called fast machine learning. For example, pruning, which maybe you're familiar with just from the ML perspective, where I'm just going to get rid of the nodes that have really low weights because they're not much influencing my total loss anyway. That saves me some math. And we can also do quantization, where I'm just going to take a blurrier image of all of my weights and biases, or maybe even my inputs, and maybe retain the core information, but again, just having fewer bits that have to go through my computational pipeline. So there are lots of different tricks that one can do if you're trying to deploy a machine learning algorithm on some custom hardware, and then care if you care about, say, latency and resources in your implementation. And so the very quick answer to that fundamental question, can I run an autoencoder in less than 25 nanoseconds? The answer is yes, if you cut a lot of it out. So the final autoencoder that we put in the Atlas trigger, we completely chop off the decoder. So we train it encoder to decoder, but then when we evaluate, we only evaluate to the mu in the latent space of a variational autoencoder. That's the only information that I need to do a decent enough job at recognizing anomalous new physics. And then we also quantized it to it's 10 to 15 bits, depending on where you are in this model. And it does get your latency down to below 25 nanoseconds. So we successfully got this into the Atlas Trigger FPGAs. It's running as we speak. And I really think the trigger, it shouldn't be underestimated how much this impacts the physics capability of a machine like the LHC, because we're recording a set of events that have never been seen before. We've been producing them at this certain collider. We're getting below those energy thresholds. This is really new phase space that's going into our data set. So of course we want to do the analysis on this data set as soon as it's collected. Okay, and then maybe just one
So,
PR flag. Yeah,
sorry,
yeah, tell me.
another question. I'm not quite familiar with this, but I'm thinking, is that the case? Like, if you make your machine learning model a bit more complicated, that means it takes more time. Does that mean you can compensate it by parallel more GPUs or CPUs or whatever hardware?
You mean can you get around like could you make an implementation on a GPU that was so parallel that it took a lot less time?
Yeah, like your model can be a bit more complicated, but you just need like larger hardware or more hardwares to compensate it. So
Yeah, so you certainly can within within certain applications.
certain application.
You the general guideline that we use is that if you want to get below a millisecond, even the most parallelized GPU in the world is not going to do it for you. And that's really getting into like what is a GPU, right? It is a we're talking in the end about shoving bits through transformers etched in silicon, right?
Huh.
And a GPU is a little less flexible than, say, a CPU. A CPU is completely reprogrammable. You can assign any of those transistors to any computational task. So,
Mm,
like on your computer, you can open up an image editor and a terminal, and you can do whatever you want. But a
yeah.
GPU has these sort of blocked out resources where it is fixing some of those transistors. They're not completely flipping as much as you want. They're ascribed to certain tasks. And that
Mm,
makes it more efficient for some of these parallelizable things.
I
If I
see.
go to like an FPGA or an ASIC, like a chip, I'm
Mm,
losing flexibility along the way because more and more of that hardware is literally etched into the silicon. I cannot reprogram it. But because of that, you're not wasting energy flipping all of these configuration bits.
I see.
So that's what makes it, that's like the hand wavy way to explain why they are fundamentally faster. Like when you're
Mm,
talking about how electrons are passing through this piece of silicon, they are
mm,
going to be more power efficient and faster than more flexible architectures.
I see.
Um, so yeah, so there's a benefit to, and there's so many of these things. Like I'm sure you guys have seen, like now there's there's GPUs and LPUs and TPUs and FPGAs and eFPGA, there's lots of different kinds of hardware platforms that are,
Yeah.
and the reason that NVIDIA is a $4 trillion company is that they can design these things to let people do, the most machine learning possible. So the hardware platform is super important, I think, And you just have to very well understand the constraints of your particular goal.
I see. Thank you.
Cool. That's actually a nice lead into this last slide I wanted to show. So we do quite a bit of R&D in my group at SLAC into different options for deploying machine learning in some of these, let's say like we use the phrase edge applications, edge referring to like real time or close to the source of the data, where you care about things like latency, power, resources, efficiency, et cetera. And so there's a great engineering team at SLAC that we're working with to look at fast, low power AI, which is relevant to the collider because of our, issues with the data acquisition. But of course, everybody wants to do faster, lower power AI to save money in their data centers. And so I think this is applicable to lots of different stuff. And we're looking into, in particular, this idea of an embedded FPGA where you're developing an ASIC, an actual microchip that has these block resources implemented in it. So it's a chip that you can reconfigure. Usually when we tape out or design a chip, it's like you etch that algorithm into the silicon and you're done. But if you can reconfigure a chip, you've got a way smaller package with way less power, but you still can do digital logic with machine learning. So this is just a group. This is a picture of us with our little test board. My PhD student Kenny, and one of the engineers Larry. That we're also working with on this. Okay, cool. So I think it's a really exciting time for both AI and particle physics, and of course the overlap. I think particle physics is a unique represents a lot of unique applications that are not necessarily covered by industry, and that makes for really interesting lanes of AI development. So of course there's a lot of new physics potential at the LHC, and of course we hope to maybe one of these anomaly detection searches will turn up something exotic. But we also have interesting data sets and problems for these cross-cutting technology areas of both AI and advanced silicon microelectronics. And so this is just a link to, I wrote a public feature that talks about a lot of different AI applications in the Atlas experiment, if with lots of nice references if people want to read more about this. Okay, thanks.